conflict with the meeting in the dean's office, so I will not be able to attend office hours today, all right? So office hours today are canceled. If you want to touch base, send me an email, set up an appointment, or I'll see you on Monday, okay? Monday, Tuesday, or Wednesday of next week. But again, office hours will be canceled today because I have a conflict with the meeting. Any other questions before we get started today? All right, let's go forward. So, we're walking our way through the microevolutionary process. What's the first step? Variation. What are the sources of variation? Mutation and recombination. Very good. In terms of those sources, what is the primary source? Mutation or recombination? It's mutation. So when we look at mutations, what is the large mutations referred to as? Chromosome mutations. The much more common mutations? Point mutation. Which one is usually lethal? For animals at least? Chromosome mutation. Which one can be beneficial, maladaptive, or neutral? Point mutation. What are the types of variation? There are three of them. The types of variation. Normal variation or continuous variation. What else? Polymorphic variation, which occurs in what kind of units? Discrete units. And then number three, ecogeographic variation, which is variation along the what? A line of ecology or geography. Those are the different types. When dealing with recombination events, just because they consider them to be secondary sources, it's kind of a misnomer. Are they not important? No, they're radically important. The difference between a mutation, however, and recombinations, mutations create what? Brand new alleles, whereas recombination just does shuffling. Very good. What if it was sexual selection between two similar organisms of the same species? Genetically, what would that be? Be crossbreeding, but it's not crossbreeding, it's what? The same genetic, similar genetics. They are inbreeding. Right? Sexual reproduction between individuals that are dissimilar genetically within the same species. Crossbreeding. Sexual reproduction between two different species. Hybridization. I prefer the trait just because I do. Sexual selection. Between a male and a female, this will often result in what populations? What will it result in? Dimorphism. That's exactly right, dimorphism. Okay, good. So that's variation in a nutshell. Then we started talking about natural selection. So variation leads to, or variation is selected by natural selection, right? So natural selection will sort out the best variants and weed out the ones that are maladaptive for any particular environment. So in dealing with natural selection, you need to have an understanding of fitness. So to be fit means what in terms of an evolutionary sense? It means you're well adapted to your environment, which means you survive and reproduce. Very good. All right. So what is the difference between evolutionary fitness and relative fitness? They're the same basic thing, but relative fitness is what? A measure of evolutionary fitness. Very good. So remember, evolutionary fitness is simply the contribution an individual makes to the pool of genes of the next generation relative to another individual. However, relative fitness is the contribution of a genotype to the next generation compared to a contribution of an alternative genotype at the same locus. So one is a measure of the other. So I gave you a brief example using wildflowers. So based on the reproductive output, you set the allele set, the genotype with the highest reproductive output to a 1. All other genotypes are divided by them. Could you do this if given this example on an exam? Yes, you will see examples of this tomorrow as well in the computation sets. All right, survival and reproduction. We can take a look at this graphically by representing a continuously variable trait and then examining versus who has the most offspring to pass on that trait to the next generation and who has fewer. And we denote this with pluses or minuses. So there are three basic types of natural selection. One of the most common requires a constant environment and organisms are well adapted to that particular set of conditions. what would this most likely lead to in terms of selection? Stabilizing selection, very good. In this case, are the extremes or the mean selected for? The mean is selected for, and the extreme phenotypes are selected against. All right? So graphically, if we were to start out with a unimodal curve, where would the pluses be if it was stabilizing selection? In the middle or on the extremes? They'll be on the middle, and over long periods of time, generational time, what will the curve look like? It'll get higher, meaning more individuals bear the mean in terms of their phenotypic characters. And what will happen to the sides? They'll close in. They'll get tighter where the extremes are being selected against phenotypically. All right, what was an example of this? Human birth weight was a nice example of this. So remember, how would I test for this on an examination? I can either give you a graphical representation and say, what kind of selection is this? Or I can give you an example. I can say within an X population, this and this is happening, and then I expect you to tell me what type of selection is in operation. So example, something like this. Over multiple generations, the height of giraffe have not changed. The environment has remained relatively constant over the same amount of time. Short neck giraffes and super long neck giraffes have been selected against. This would be an example of stabilizing selection. So be prepared. Remember how the college examination was primarily example-based? So will this. So we'll give you a series of examples and say, take what you know and tell me what you can apply. There'll be computations in the same way, though, but not as computationally rich as the ecology exam was. All right? Remember, in terms of computations, we'll come back to this as well. Should you know how to do the Hardy-Weinberg equilibrium? Yes, do not blow that off. It will be on the examination. Plain and simple, right? There's no mystery there. You'll see it in a variety of forms. So be prepared for it. What if I was to tell you that the environmental and biological conditions were changing over time? The organisms were not well adapted to that change. Most likely this would result in what kind of selection? Directional selection. Very good. So in directional selection, you're not selecting for the mean phenotypic character, you're typically selecting for what? One extreme or the other. Both at the same time? No. One or the other. What's the time scale here? It's long, multi-generational again, right? So in this case, if I was to give you a graphical representation of it, where do the pluses and the minuses fall on the unimodal curve? They're on one side or the other. Depending if they were all on the right side, what would happen to the curve over time? It would shift the phenotypic character in that direction. I gave the example of the brown bear here, correct? So when the periods of glacial periods were very cold, what was the size of the bear? They shifted and they got larger in terms of their biomass. As conditions warmed climatically, what happened? They shifted back the other direction and they got smaller. Energy conservation and heat warp was basically the traits that were going hand in hand with the large increase in body size or the decrease in body size. I gave you a nice example dealing with the peppered moth. Peppered moth is a very clean example of directional selection and operation. What are the two colors of the moths? They're white and they're black with gray speckling. So, before the Industrial Revolution, what was the majority of the population colored? They were white. During the Industrial Revolution, they were black. And then afterwards, they were white again. What was the selective driving force here? It was a combination of things. It was pollution of the environment, right, by coal, which put silt down. But what was the selecting agent along all of those? The one common thing was predation. Predation by what? Birds. So birds dictated which was the best fit, which was the best variant for that particular environment. When the bark was nice and clean and it was full of lichens, because pollution was low, which was selected against the more? The black was, because it was easy to pick out against the white trunk. But as soon as the environment shifted, now which morph was more beneficial? The black became adaptive, right? Because the birds had a harder time seeing it on the polluted trunks, but as soon as the thatch was scrubbed, that cleaned up the soot. Now the trees got white again. What's the selected morph? It's white. So the birds were the driving evolutionary force here in selecting which variant was most fit. Was it lucky that the population had variation in color? Absolutely, because without that variation in color, what would have happened? Birds would have driven them to extinction. Okay? So it was that extra variant that allowed that population of moths to subsist through time and maintain species persistence. Can this be replicated in a laboratory? It can be replicated in a laboratory, it can be replicated in natural experiments, and I gave you an example of the kettlewell experiments, right? Did exactly the same thing by releasing moths and catching them. So basically when they release moths, you catch more black moths from what type of habitats? Polluted habitats. So what happened to all the white ones? They got eaten. And where do you catch from the unpolluted habitats? More white moths. Why? Because all the black ones were consumed. So it basically tests the natural experiment and gives exactly the same results, displaying directional selection in a time scale which we can view and observe. All right, I gave you a couple more examples. So we drive directional selection all the time because of the things that we do in terms of our food crops and our domestication of animals. And so one of the problems we have is that we want to increase the yields of our agricultural crops. In order to do that, we want to get rid of the insect pests that threaten them, that take the yield down, and why we do that with a series of synthetic pesticides typically. The problem is, you wipe out everything. Never. Who's left? The resistant forms that bear the phenotypic characters of resistance to the chemical, they repopulate, and then you hit them again. You kill even less of them. After about 2 or 3 applications, they're completely ineffective. The other big problem with this is, who do you kill? You kill the predators of the pests, which you want to be there because their population sizes are smaller. And what do we know about smaller population sizes? They're much more likely to go what? Extinct under environmental pressure. So we're creating a synthetic environmental pressure, an artificial one which can drive them to extinction quite quickly. So what is that called when you eliminate the predators of the pests and the pest comes surging back? Pest resurgence, and that happens quite a bit. We see it around us all the time in terms of antibiotic resistance, which is a pressing problem for us as a civilization. So because of the misuse of antibiotics, the bacteria have rapidly developed resistance to the different types of antibiotics that we use to treat them. What gives them a major advantage here? Yeah, they have rapid evolution because of asexual reproduction, the ability to share their genetic material. The second thing they have is we're idiots. That's simple, right? We've misused the gift that we've been given. So those two things, their ability to evolve quickly and our inability to do the right thing with the drugs that we've been provided, have basically allowed them to counteract almost everything we've produced. And that's not good for us in terms of our survivability and our health. How many of you have taken antibiotics in your life? Is there anyone who's never had an antibiotic? I doubt it seriously. And if you think you have, talk to your parents. I'm sure they've given it to you. Many of you would not be here today without antibiotics. Many of you would be dead. It's that simple, right? Those simple infections that you got rid of with a couple pills that could have taken your life quite easily. So it is a big deal. If you're going into medical sciences, it's something to really think about. All right, disruptive selection is another one. Disruptive selection is easily identified from the other two forms of selection because it's a short time scale. That's exactly right. And what else about the curve is different? It produces a what? A bimodal curve. That's exactly right. It's a short time scale and bimodal curve. If you were to see that graphically, instantly identifies it as disruptive selection. So what are the environmental conditions? They're switching, they're changing rapidly, okay? It's a period of rapid environmental change is the primary environmental condition which drives this form of selection. In this particular case, you select against the what? Phenotypically? The mean, the middle, and then what do you select for? Both extremes, okay, both extremes. So I gave you an example of this, which was the black-bellied seed cracker finch. What size bills do they have? They have big and they have small. What do the big ones eat? Big, large, hard seeds. And the small ones? Soft, tiny, soft-bodied seeds. Can the big-billed birds eat the small seeds very well? No. Can the small-billed birds eat the big seeds very well? Nope. Why isn't there any intermediate-sized bird, Bill? They can't eat either well. So remember, why is this a form of disruptive selection? Because you have two extremes selected for at the same time, not the mean. And what's the environment doing? It's rapidly changing back and forth between a wet environment and a dry environment that burns. During the dry season when it burns, who's doing best? The big-billed bird. When the season is wet, who's doing best? The small-billed bird. So before the large-billed birds are ever driven down too low, what happens? It flips, and vice versa. Why doesn't the intermediate-billed bird persist at all? It's bad at both. That's exactly right. So that's a nice example of disruptive selection. All right, that brings us up to speed, and I stopped on this slide. And the reason is I want to spend some time talking about this because it's really an interesting discussion. So yes?
Do you ever see a bimodal curve without, like, just like a disruption that happens?
Typically not.
Okay.
There's some kind of disruptive force that's in operation to create that bimodality. It's a good question. All right. So when we think about evolution, you often hear this statement. So I used to go and debate evolution quite a bit. I don't do it much anymore because it was such a frustrating experience. And I know that's not good for me, and I continue to do it to educate, but sometimes it just gets infuriating. Because sometimes ignorance is pretty tough to breach, you know? And there gets to a point where people get to a certain point in the discussion of evolution where they just say, I believe it. And once you reach a point in the discussion like that where you just believe something because you do, I'm kind of at a loss as a scientist to get past that, right? It's kind of like you just put your feet in the sand. I'm not going, I believe it. Well, why? Because I do. I have to go. Right? But I can't do anything more at that point. It's really difficult. So one of the things you often get is this idea here. Well, why aren't there just perfect things on the planet then if evolution is in operation? Well, because evolution doesn't work that way for one thing. So if natural selection is producing organisms best fit to their environment, the basic question is, can you engineer a perfect organism? That's always a question you get. Where is there a perfect organism on this planet? Because it doesn't work that way. And so this is basically why this cannot occur. Do I want this to occur? I don't even want that to occur. Because as soon as I become, I don't even know what really that means, but if you had an organism perfectly fit for this particular environment, what's the problem?
Environment changes.
As soon as that environment would change in just the slightest bit, what would happen to that organism? They would be extinct like that, the entire population of whatever it was. So this is not a good idea. This is some kind of weird pinnacle of achievement. There's nothing to be achieved. This leads to your ultimate destruction, all right? So it's not a good thing. So let's talk about why natural selection can't create a perfect organism. The first thing is this. The answer is no, but why? So the first thing is natural selection can only edit what's already there, right? So basically, natural selection is looking at all the variation in a population, and in a given environment, it is saying what is best fit for it, and what is maladaptive, and what is neutral, okay? So it basically starts from an existing place. It selects the fittest phenotypes in the population that currently exist. They may not be the best. They may not be ideal. It's just you're better than that, or you're better than this, and so you get selected. It's not perfect. That's number one. And the second part is those additions, right, those existing variations had to come from someplace. So they have a long historical record going back, which gives them a constraint in time. So evolution is limited by historical constraints. It had to be built from someplace in the past to get you to where you are now. So it's not like you just instantly invent a brand new complex structure because you need it. Like a classic example that I used to give, and I get in the big arguments about, is for people who are debating the idea of evolution, you often get this statement they'll say. This one comes up quite a bit. And it's like, there's no possible way that the human eye could have been actually developed over time. It's much too complex for that, right? It had to be a pre-programmed plan that was put into place. And I look at that and I just go, what the hell did you just say to me? I mean, is that an accurate statement? It's absolutely false, okay? And it's kind of ludicrous to state that we have an amazing record of the development of the evolution of the eyeball. And so what's great about it is, because there's lots of things with vision on the planet, first of all, holding the human eye as kind of the pinnacle of sight is completely idiotic, because is it? No, there's 101 different organisms on the planet with much better eyeballs than we have, okay? Ours is kind of a mid-grade eye in terms of what it is. People have all kinds of misconceptions too, like color vision. Wow, color vision, humans. Lots of things have color vision. Fish had color vision way before we had color vision. So all those things are kind of ridiculous. But when it comes down to this idea of the complexity of the eye, I can literally point at organisms today that are living that have all the precursors of the complex eye that we have today, and I can trace back in the fossil record and see similar things that are holding it on. So I can see the photosynthetic, I have photoreceptor pigments in the eye. I can see things that just detect light and dark. I can walk through all the kind of environmental features that would produce these particular things and how they would change over time, be modified, and be useful for particular environments. It's not really that detailed at all. But what's nice about it is there's this big, long history going way back when about simple cells that were photoreactive and how those simple photoreactive cells can be basically put together, organized in different ways, different physiological mechanisms go into play for what they do. And you can go all the way up to a nice complex eye that we have today. But the historical constraint is really important. You just can't say, I need an eye. I'm mutating a brand new, gigantic, fully formed eyeball. It doesn't work that way, okay? So you can't build complex structures from scratch. You take existing things and then you modify them and adapt them to new situations. Here's a really important one. Adaptations are often really big compromises. So, like a perfect organism would have like the best of things. Let's say I wanted to run and I wanted to fly. Okay, well that's great. But that's really tough to do. Is there something like the Pegasus around today? Remember, like the Greek horse did that, right? It could run and it could fly. But it had wings and it had what? It had 4 legs. Do we have anything like that on the planet? No. Because when you look at the basic body plan of organisms, they're pretty constrained from what their historical constraints were, their ancestors. And so typically you have things that are quadrupedal in nature when you get to the complex animal systems like ourselves. Or bipedal, but we still have the 4 limbs, we just modified them for different things. So when you take a look at a bird, well, it took 2 of those limbs and made them into wings, okay? So evolutionary time has developed the wing, which is basically, do birds fly purely with the hand or their arm? It's just a strut to hold what? The modified scales, which are the feathers, which are actually the flying devices, okay? But that's a compromise. You ever seen birds try and walk around? Do they do a very good job of walking? Well, they're terrible walkers, especially birds that are good flyers. So in order to fly, certain things have to be given up that used to be good for running. Because you've given up, first you've given up the limbs. And then to fly requires all kinds of structural changes. Everybody's talked about structural changes in the human being to create the gait, how it did weird things to our jaw structure and stuff like that. Same thing for birds. So when you look at birds, notice that first of all, birds have relatively short bodies. They're very short and stout. Their wings are very long. Their heads can be quite big, but their bodies are quite stout and reduced. The reason is if birds are really long, what happens every time they take a downstroke? What happens to the body if it's long behind them? When I stroke like this, what will happen to the body? What's the counterforce? It's up, so it'll flip the body up at the back. And if I do that, what happens to me in terms of my efficiency of flight? I'm burning tremendous amounts of energy. It's wasteful. It screws up all of my aerodynamics. So what you typically see is birds have fused the vertebrae in their back so that it doesn't flip anymore. They become reduced and compressed, and then they fuse the vertebrae in the back, and that stops the back flip. But what have they given up? They're much more aerodynamic. They waste less energy to fly, and flight is the most energetically costly form of locomotion there is, because this is a non-dense medium, right? It's tough to fly against. So what do they give up, though, when they do that? If you fuse your spine, ever seen anybody get a spinal fusion before? When you get old, you'll get somebody will get a spinal fusion. It's because one of the things that screws up in human beings is our back, because bipedalism screws up our spinal column. And so you compress the discs, and if you start to pinch the discs, you get all kinds of spinal pain, your legs will numb up, all kinds of stuff like that. And so a lot of times what they'll do is they will basically get rid of the disc and then fuse the vertebrae together and lock them into place. But as soon as you do that, what do you give up? You give up the ability to bend and all that flexibility. Well, the birds have done it for flight. So if you've seen them, they do that weird kind of stilty walk thing. That's because they can't bend their vertebrae the same way that we can. So that makes them very inefficient on land. Now there's some that haven't done that, like the others have gone in different directions, like the ostrich and the emu. And those can run amazingly quick. But they've given up what? They can't fly. So it's one way or another. So those are compromises that you make. Here's this sea lion, right? Or a sea, looks like harbor seal, not a sea lion. But what does it have? It doesn't have a hand anymore. It has a flipper. So these are aquatic organisms. They're basically mammals that basically return to the sea. Have you ever seen them walking around on land? Do they do a good job of it? They're terrible. Take a look at a seal next time. Look how they walk on land. They have to drag their hind limbs behind, what's left of their hind limbs behind. They're kind of shuffling on their front flippers. Terrible. They're not good runners at all. Sea lions are a little bit better because they can still swing their pelvic girdle underneath them. They can kind of waddle on both their pelvic girdle and their front flippers and do a pretty good job. But seals are really bad. They've lost it almost completely in the back. They can't support themselves down the way. So on land, they're miserable. Are they easy to hunt? That's why they were almost exterminated by hunters for their blubber and for their fur, because once they're on land, they're easy pickings. They can't run away. However, stick them in water, what do they look like? Oh my gosh, if you want to feel stupid, right, go swim with sea lions. The water is an interesting thing for human beings. When you get in it, you feel all nice and everything's great until it's not. And so, one of the things about it is if you ever dive with sea lions, they'll make you feel like idiots. Because in the water, they are so amazingly agile with the modifications of their body that they have made with the flipper systems and the way they're streamlined. And they're just flying, darting around you up and down. And it's a really crazy experience. It's kind of humbling. You're like, yeah, I suck. I get it. I suck. I'm a terrible swimmer. You're much better than me. I'm really bad. Thank you. And they really make you feel bad. They're also going to be quite territorial. The males can be quite aggressive and they bite. Getting bitten by a sea lion is not fun. It's like getting bit by the worst dog you've ever experienced. And they kind of bark and do the same kinds of things. It's pretty nasty business. So the take home here is it's a compromise. In order to be that great of a swimmer, they've given up all the advantage of walking on land. Your body is an amazing set of compromises. Human beings have developed incredible flexibility in the joints. That's why we break down so easily. How many of you guys have taken joint injuries? How many people have had bad knees, or the ligaments in the knees have gone out, torn a meniscus? Right, so I used to surf Pelly. I've torn everything possible everywhere in my knees. Okay? You name it, it's gone. So, literally, it is done. And so, what are we giving up for that flexibility? Strength and duration power of those elements, right? So, we could do all kinds of fine-scale manipulations. Remember I talked about how the chimpanzees with the finger touching and stuff like that? No problem for us. We do all that stuff, easy manipulations, all kinds of flexibility, but we've given up tremendous strength and things break down over time. And so we're prone to all these kinds of injuries that other animals are not. Compromise. Flexibility comes at a cost. So adaptations are often compromises. You get really good at one thing, you're going to get crappy at another. That means you're not perfect, right? Because it's all compromise. And then the last one, which we hardly ever think about because of the way it's typically presented, evolution typically presented, is the idea of chance. Chance is so strong of an agent in the evolutionary process because chance things happen every day, all the time, and it often happens to the most fit variants. So here's the thing. I could be the best fit individual in my population and have the most robust set of phenotypic characters because my genotype is so well suited to that particular environment. And I strut outside and a rock falls on me, or a bus hits me, or whatever it might be. Or I'm the chief bug of the bug kingdom, and you happen to stomp on me on your way to class, right? That chance event means that you get weeded out of the population. It didn't matter how fit you were. Chance weeded you right out. And so what happens then? What does natural selection do? Oh, well, what do I pick? It's just never next best. That's right. That's exactly what happens. So the top dog is gone. I just go to whatever's right next in line. So all of these things add up, and then the environment interacts with chance all the time. So basically what you get is, it's not perfect, it's just better than. That's how it works. Evolution is not the best, perfect, it's just better than. Which is great, because all these little things that you have, all these strange little variations, stuff that might not be perfect now or whatever, doesn't do quite a good job, flip the environment a little bit, and lo and behold, it might be the best thing there is for that particular change, right? So, does evolution create perfect organisms? No, it can't. You have to start in some place. Where you started came from someplace else. Adaptations are often compromises. Chance has a big impact with the environment. You don't get a perfect organism, and you don't want one, because if